Hello, friends. This presentation is a complement to a presentation that by the time you're listening to this will have been given at the 51st College Chemistry Canada Conference. So my thanks to the organizing committee of this particular conference, which was held at Simon Fraser University. This talk is a convergence of three things for me at this point in my career. Number one, it reflects my sincere interest in understanding how students learn chemistry. What are the impediments to how students learn chemistry? And in a sense, how do they use those symbols and representations that are unique to the nature of chemistry? It also reflects my passion since almost the beginning of my teaching career in exploring online learning assessments. My interest in understanding how can these online assessment tools help students engage in formative assessment to support their learning. The last thing that this talk reflects is my sincere gratitude and admiration for my colleague Carl LeBlanc, who is the designer of the Open OChem platform. And if I may say, although I am doing the talking, in a sense, 99% of the work that I'm describing here is his work, and 1% is my minor contribution. So let us start with the following. So anyone who has studied chemistry, and then especially those that are in the field of chemistry education, will recognize this kind of question and recognize the corresponding answer and understand that it really does tie to the symbolic representations that we use in chemistry. So draw the Lewis structure of formic acid. And so we start from a condensed structure and then being able to translate that into this Lewis structure, which shows as these dashed lines representing pairs of electrons, representing the covalent bond. We've got lone pairs, even just the symbols that we use to represent the elements. We all take these things now for granted. But as a student learning chemistry, these are things that students need to learn and, in a sense, master. Now, what I'm showing you here is a question that was taken from a department assessment quiz. This department assessment quiz was given by a university in Virginia. And in a sense, they had 5 different questions. And they gave these questions to students over a period of 8 years in the 3rd semester of the student's career. So the students in general will have taken 2 semesters of first-year chemistry, and they're in between their 3rd and 4th semester of organic chemistry. And it was to get a sense, where students are at before they enter into their 4th semester. Over the course of those 8 years, different professors, instructors would have taught the course with different pedagogical approaches, and the department just wanted to get a sense of where students were at. So this was one of the questions that the department asked. Here's another question where you can see that it's taking a name of a compound, ethane, and asking students to translate it into a Newman projection. Note that it's a staggered conformation. So these are things that students would need to understand further. This is a 3rd question. And there were 2 others that were like this that I'm not going to show you here, where they're definitely at a higher level, being able to use curved arrow notation to show mechanism. We're showing formal charges by the negative and plus. We're showing wedges and dashes to show the stereochemistry. We're using bond line drawings to represent rings. And there's a whole lot of things going on here that students need to master in order to be able to solve this sort of problem. The paper describing this study was published in the Journal of ChemEd in 2019. And in the study, they indicated that essentially there was no difference in the student performance over those 8 years. And further, students struggled even with those first 2 questions where at least 1/3 of the students got something wrong. In terms of this kind of question and the 2 others that are like this, 95% of the students did something incorrectly. So it really pointed to the investigators that these are challenging things for students and perhaps we need to try to address it. I took this quote from the study, and you can see the reference at the bottom there. I'm going to pause here for a minute to ask you to read this quote. Some of my takeaways from this quote are that as students learn the chemistry content, they're doing that through the process of actually learning how to interpret and apply representation. And by so doing, then they're learning how to talk chemistry. And this is unique in a sense to the nature of chemistry, these symbolic representations. But what I find actually really kind of cool here is that there's also that in being able to interpret symbolic representations, this involves the skill of information processing, the evaluation, interpretation, and transformation. And these are transferable skills. So by learning those things that are unique to chemistry in order to be able to learn the chemistry content, there's also this learning of information processing, which of course is really important for our education of students, regardless of which discipline they go on. Now, given, however, that many students are struggling with this, we might think, well, what can we do? How can we guide students? Over the course of my career, one of the things that I've been very much interested in, as kind of alluded to, is assessment, and in particular online assessment. Now, I do collect pen and paper assignments. I think those are important because then you can see what students are able to actually write down and draw on things. I just want to go back. If we take a look at, for instance, the third question, the second question, and the first question, you'll see that all the question describers say draw, 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 draw. So the students actively need to answer these questions by drawing something. So yeah, I can kind of get at that when students are handing in paper assignments. That said, I'm really interested in students being able to do online. And the reason why I like online so much is that then the students can get immediate feedback. And in terms of online, if the students are presented with online problems, they can answer way more questions than I could ever try to assess by paper assignments. Kudos to publishing companies who have developed beautiful online homework systems. But I like writing my own online questions, in part because I'm saving some money for the students. And secondly, I can then tailor the question more to how I present the material in the course. And I believe that makes it easier for students to make the connection between the assessment and then what's done in the course. But by around 2019, I was essentially making these quizzes in Moodle, and this was sort of where we were at. And you can see here it says, select the best Lewis structure for the molecule acetone. So that's a different process than being able to actually take that condensed structure and draw the Lewis structure from scratch. So I realized there was limitations to my Moodle quizzes. And then at about the same time, COVID hit. And I'm thinking, it's going to be a lot harder, especially with online teaching, to be able to see what are students actually able to draw? What are they able to do? So through a series of very fortunate situations, I stumbled on the platform designed by Carl LeBlanc, and he calls it the Open OChem platform. Let me just show you an example here. So here we have a draw editor, and now we're drawing the Lewis structure for the molecule acetone. And you'll see that, I finished drawing it, and then I put in one lone pair just to show you that that's wrong. You need to put both lone pairs in on the oxygen, and then that will be marked correctly. And one of the beauties of this platform is that, yes, there was a large bank of questions already made, but it's also such that I could make my own questions. And make my own questions where I'm asking students to draw structures, and it assesses that. And so when I found this, I was like, oh man, this is so amazing. And this is exactly what I need to sort of develop an online assessment tool for my students, both COVID and then thinking going forward. This is an example of a Lewis structure. So take, for example, here's one of my questions in a Moodle quiz, where I want students to associate a name with a bond line drawing. And going back and looking at my Moodle quizzes, I see that essentially all of them involve taking a structure and then correlating it with a name, or maybe even typing in a name, because it wasn't so easy to draw a structure given the Moodle platform. But now I could take, for instance, the name and ask the students, so this is the same name compound, ask the students to draw that structure. And so here we have a little bit of an animated GIF just showing being able to draw that structure. Again, this opened up a huge opportunity to ask students not only to be able to name compounds, but be able to draw them. But speaking of naming, I also discovered in the OpenOChem platform that Carl LeBlanc had designed these scaffolds to assist students to be able to start to think about what's involved in naming an organic compound. And anyone who's taught this knows that it's a challenge to get the students to really pick out all the fine details. And so by selecting from a menu, in a sense, it helps guide students to think about systematically about what's involved in naming that compound. Again, a whole bunch of these questions can be designed by the instructor and then associated with their learning management system to assess students. Here is a question that comes from my Moodle quizzes where I'm drawing Newman projections, or I'm drawing the Newman projections and I'm asking students to be able to pick which Newman projection corresponds to the most stable conformation of 2,3-dimethylbutane. Well, it would be better if I could actually ask them to draw the most stable conformation of 2,3-dimethylbutane. Well, sure enough, Carl had this feature of this kind of drag and drop and being able to choose this Newman projection either in the staggered or in the eclipse format. And so again, I think this takes a different sort of information processing ability for students. And we're able to directly assess this for students and give them multiple problems. Things related to stereochemistry. So for instance, a pen and paper assignment, I might give a student a molecule and draw and then pick out the chiral centers. If it's an online assessment, you may be more likely to say, well, how many chiral centers are there? You don't really know that the students are recognizing which particular centers are indeed chiral. But sure enough, in the OpenOChem platform, there's this select feature. So given this structure of a steroid, and students can go around and highlight those carbons that are chiral. And then thinking about reaction mechanism, reactions, products. Often my questions in Moodle were something like this, where I was asking students to anticipate the product. Now, admittedly, I could draw some of the structures showing stereochemistry. In this case, it's assessing the regiochemistry of the outcome. But it would be nice also to be able to assess the mechanism for this particular reaction. For instance, in OpenOChem, there is this curved arrow assessment feature. Now, I'm drawing a templated version of this particular reaction, although you can actually set the students loose to draw the complete mechanism. It's hard to anticipate exactly how they're going to approach the reaction, so it's more realistic to give them this sort of template and practice the curved arrows. But that said, for instance, in this sort of question, we're asking students to predict the product of the dibromination, and they really do need to worry about the stereochemistry because this reaction is in particular stereospecific, where only the meso compound of brominated stilbene is formed. And so that would be reflected in their answer here. And going forward, still thinking about this using online assessments and being able to get at the students' thinking in terms of organic chemistry. It's like, well, how can you do that? And so in this particular case, it's thinking about how we go from benzene to form a di-substituted benzene. And anyone who's taught this knows that there is a particular order that this needs to be done based on the directing effects of the substituents, based on whether or not the ring is activated or deactivated, whether or not you get a Friedel-Crafts reaction, that sort of thing. And so I designed this question where I threw out all the different relevant reagents that the students had learned about, and I thought, okay, well, they can show me the synthesis by listing which reagent they would use first, and then next, and then next. When I designed this, I was pretty excited, so I shared this with Carl LeBlanc and said, hey, look what I did. You might be interested in this. And he was very gracious, yes. And then he said, but I think I can do better. And sure enough, he did way better. So this is a synthesis a templated synthesis sort of problem. And by the way, the person inputting the question here can decide what is shown and what needs to be filled in. The larger boxes are structures that you draw in, and those arrows with question marks would be the reagents that would be necessary. So you can scaffold this quite nicely. And instead of giving the students the fact that they need a 2-chloropropane structure to add isopropyl group to benzene, they need to draw it themselves rather than pick it out from a list. So you can see here, this would be the corresponding outcome of inputting the various answers. Around the same time, I started to play with, learn how to use H5P. And what I mean by around the same time, so this was all around the time of COVID, thinking about online teaching, learning how to use the OpenOChem platform, writing a lot of questions for the students for the organic chemistry course. But I also turned my attention to general chemistry and using H5P and thinking, how can I use this platform to support the student learning? And one of the nice things about H5P is they've got this really easy drag and drop type of question, easy in the sense of easy for me to make. And I was thinking, well, maybe I could scaffold how students do a factor analysis conversion type of problem. So this is a simple density type of problem where we're starting with a mass and transforming into a volume in liters. And you can see that the students have a choice of different conversion factors. And so a completed problem would look something like this. And again, I was pretty proud that I'd come up with this and was excited to, let's say, share with Carl. You know, I have no programming ability, but I thought, it was kind of a cool approach. So I share this with Carl, and sure enough, he comes up with something so much better. So this is in OpenOChem. You can see that we've got essentially this blank box. In the stem of the question, we have these numbers that are surrounded by a dash rectangle. And if you click on this, it will insert them into the box here. Here, for instance, is how you would solve this particular problem. So it's just a little animated GIF. So I let it play through so you could see the various things that need to be done. You can put out the 50 kilograms, and then you need to choose the appropriate conversion factors. If it's not a typical kind of conversion factor, such as the density, for instance, then you would input that in the stem of the question. You can see that it allows students to see the canceling of the units, and then finally the numerical answer with units. So you can imagine stoichiometric type of problems, you know, anything that involves these sorts of conversions. And then, of course, thinking about things that are unique to chemistry, the mole bridge, thinking about a molecular formula representing a whole bunch of conversion factors. Formula for glucose, C6H12O6. And of course, those subscripts represent the number of atoms that are in one molecule of glucose. But those are conversion factors, and that can be built into this kind of problem. You know, how many carbon atoms are in 1 mole of glucose? And I think it really makes it apparent to students on how to do this kind of conversion. And you can write these all yourself. One of the other things that Carl developed in the OpenOChem was this also a drag and drop feature. He made it very easy that you could either draw a diagram directly in OpenOChem, or you can import a diagram. And so in this case, I imported a diagram of an ICE table, and I wanted to simulate students completing an equilibrium ICE table and then coming up with the equilibrium constant. Now, in part, I wanted to do this because, for instance, if students just take that paragraph and cut and paste and put it into ChatGPT, the output will directly be the equilibrium constant, because ChatGPT or any other kind of AI tool can easily do that sort of calculation. So here, in a sense, it scaffolds the problem. And even if students did do that with ChatGPT, they still got to transform their information into completing the ICE tables. Completed ICE table would look something like this. So I think this drag and drop feature is very powerful in being able to scaffold various kinds of problems. Also built into OpenOChem is to be able to put little short answers and multiple short answers, and to organize all of this using a table format. So you can see I'm trying to connect the macroscopic level of doing, in this case, a particular solution dilution and the corresponding calculation. And again, if I just put the stem of this question into ChatGPT, output will be directly the new concentration. By putting it this way, students at least need to take the information and put it in the appropriate boxes to the appropriate sig figs, and hopefully make that kind of connection. That is, make the appropriate connection on how this calculation is done. And so here is, of course, the answers to doing this particular kind of dilution problem. Again, a feature of being able to put these multiple boxes in, this is a redox type of question. And for instance, other online homework that I would have had would have asked students to identify the reducing agent, oxidizing agent, or maybe assign an oxidation number, or maybe a change in oxidation number. Well, here, use this format, so using a table to organize everything, and then putting these multiple answers, I can actually see what sort of oxidation number students have come up with for each particular atom in a compound as these things get transformed in a redox reaction, and then to identify the reducing or oxidizing agent. And I use this format actually in my paper midterms and exams, so it makes the connection to the online assessment, and then the students see it on paper in their tests. That uniform presentation helps them make the appropriate connections. So here's the outcome, the answer. One of the things that I wanted to show you here, or highlight, is that for each one of these questions, I can actually write some fairly robust feedback to the students. Of course, this does take a bit of time and anticipation of what the students' errors may be, but certainly if one really wanted to go deep, one could really help students come to understand where they may have misunderstood things. So even though in the OpenOChem we can draw structures, I wanted to also assess, for instance, could they assign an appropriate molecular dipole arrow to a polar molecule? Here's one approach, is again, it uses these fill-in boxes, and I made a drawing illustrating the appropriate geometry that would be consistent with this nitrosyl chloride. I've indicated the electronegativities of each of the elements. We would expect that the molecular dipole, instead of going right through the molecule, as would be represented by letters A to E, would instead be going from letter A to D, given that the oxygen is more electronegative than the chlorine. And so a completed version of this would look something like this. I should also mention this particular kind of question where here it's a calorimetry type of problem. And, none of the math in calorimetry is particularly challenging, but there's a lot of information for students to take in. So this is a drag and drop type of problem. And I think that presenting it in this way allows students to see the bigger picture. For instance, if you think about the concentrations that are given and volumes of HBr, our acid, and then KOH, our base, that information both tells us about ultimately the mass of our solution, given the density, but it also tells us, given the concentration and volume, the amount of limiting reagent. So both of those pieces of information have to be extracted. And so that's why presenting it in this way, I think it scaffolds a bit. So I indicate, okay, we got to determine the amount of limiting reagent, we have to determine the mass of the solution, and then we're going to use this energy conservation type of formula, which we've commonly used in our lectures and then also in our lab manual, to calculate the delta H for this particular reaction, first of all in kilojoules and then kilojoules per mole. So here's the result of dragging all the appropriate boxes in. And I'm just hoping that if students see the bigger picture like this, they'll be able to more easily put it together. Again, if students just took the stem of the question and put it into ChatGPT, it would spit out very easily the change in enthalpy. So at least with scaffolding it like this, they need to think about what's involved in solving this particular kind of question. So to end this presentation, again, I really want to thank my colleague Carl LeBlanc for all his work in creating the OpenOChem platform and for his gracious generosity in sharing the platform with many chemistry educators, including myself, and allowing us to support our students, I believe, in a more effective way. I have really appreciated his partnership as a colleague. Again, though, he has all the programming skills. I'm just a user. Huge gratitude. And I thank again the C3 Organizing Committee for allowing me to present on this topic.